Hello, it's Keith here, and this is lesson 7 of the Photon series of Z80 programming tutorials. We're looking at the platform specific code, and we're going to be looking at the Sam Coupe today. So we're going to be going over this game. If you've not seen it yet, it's a simple Tron clone. We're basically controlling the pink line at the top. We can move around, we can move fast to try and catch up with the enemy. Basically what we're going to be looking at is the control code. We're also going to be looking more importantly at the PSET code. Now the lines and the dots here are being drawn with two commands, a PSET command for drawing a dot, and the point is being used for the collision detection, and that reads a pixel back from the screen. Now on the Sam Coupe we're in 16 color mode, so there are 2 pixels per byte. Not so hard, not as hard as the CPC, but still we're going to be looking at the code that is required to work with the screen coordinates. Let's go over to the code and let's have a look at this version of the game. Scrolling up to the top there. Okay, so here is the start of the code. Now the game needs about 64 bytes of memory, but we allocate a 256 byte block here for the game variables. The rest of the game can run in ROM if required, not on this system, but it is on something like the master system. So we're defining our area of memory here. We're then defining the screen attributes. Screen width 32 defines this. This is basically the typical screen size. Some use a 40 unit wide screen, but like the Amstrad CPC, but that's relatively rare. The sort of ideal size is 256 by 192. So we're defining this one which defines the scales of the object, and these which define the boundaries of the screen for drawing the lines around the edges and things like that. We're then defining 4 colors. Some systems have less than 4 colors and we have to remap some of them, but this system has 16 colors, so we can use the proper 4 colors. Very good, so that's what we're doing there. And then here's our start of our code. We're turning on the screen. We're defining the screen as being memory addresses 0 and onwards, so the first 24K of system memory will be the screen, and that means we have to disable interrupts because otherwise there'll be trouble. We're defining a palette here. We are sending these to the palette ports here. You can see we're setting C here, and that will define the colors, and the palette is being defined at the bottom. We're actually only using the first 5 entries here, the rest aren't used by this game, but we've got them there anyway. And then here is the start of the code itself, so we're wiping out the user variables here and we're starting the game with the main menu. That will show the main menu, wait for fire, that kind of thing. And then infinite loop is the main game loop, so this is what does all of the game code. Now the first thing we're doing here is we're incrementing the tick here. The tick is used to handle the movement speeds. Basically, normally speaking, the player and the enemy only move every other tick, but when boost is enabled, the player will move twice as fast. The enemy never uses boost. It's just a thing to make the game a bit more fun for the player, really. Now, depending on if boost is set, we change the delay here. The reason for that is when boost is enabled, we have to update the boost counter at the bottom, and it's quite slow because it's drawing everything with vector fonts. It's a bit of a pain, so we're having to alter the speed there accordingly. Now here's our main loop here, and this is going to read in the controls, and it's going to process any keys, and it's also going to process the releasing of a key. Now the game uses some debouncing here. If I just start the game up here, if I turn and I keep my key pressed down, you'll notice I've not turned again, but then if I release and press again, we can turn a great many times. That's not the case with boost, which is the opposite. We have to hold down the enter key in this case to boost our speed. So what we're doing here basically is we're checking if any keys are pressed here. If a key is released, then we are clearing the key timeout here. Otherwise, we just keep continuing processing here. We're reading in any input from the key presses into D here, and we're going to be processing this down here after our loop ends. So here we're checking the key timeout. If the key timeout is still set, we're going to skip over the processing of joystick key pressing because the key hasn't been released yet. What we're doing here is we're disabling boost by setting it to 1 here. You'll see it's set to 0 down here if the fire button, which is enter on this system, is pressed. Now what we're doing next is we're reading the keys and we're altering the player direction and also potentially the acceleration. So what we're doing here is we're checking for left and right here. We're decreasing the player direction to make it turn to the left, or increasing it to make it turn to the right. Now this will basically loop around below 255 and above 255 back to 0. The set player direction is actually doing the rest of the work to the player direction, and it's also altering the accelerations. So this is multi-platform code, nothing relating to this particular system. So there's not much of the apparent code that handles the player direction here. Now you'll notice the timeout's being set if left and right are being pressed. It's not set if fire is being pressed because we need to be able to hold down fire. So what we're doing when the fire button's pressed is checking if there's any boost power left, and if there is, then we're setting boost as enabled. Now the decreasing of boost power is handled by the multi-platform code, so we don't see that here. Handle player updates the human player. Handle CPU updates the CPU, and that does all of the drawing and the movement and the collision detection. So there's very little in here, which is what we want for the platform-specific part. And the infinite loop just jumps back to the start of the main loop here, and this repeats around. So that's really all there is to it. Now we've got wait for fire and read controls. Now read controls is reading in from the keyboard here using QAOP in this case. So this is, I've covered it before, it's a keyboard reading routine. If you want to see more of that, please see the Y-Quest series, in which I covered it a bit, and also the Simple series. The joystick keyboard reading in the Simple series is going to be the best one for you to look up for that. What we're really interested in today is the PSET for writing a pixel and the point for reading a pixel. We're going to be looking at these. Now, as I say, each byte of the screen has 2 pixels in it. The top nibble is the left pixel, the bottom nibble is the right pixel. So we're going to need to, basically, when we want to set a pixel, we're going to need to work out what byte it's contained in and how to mask out the pixel we want to change and what color to put in that position. So get pixel mask is going to work out the pixel within the screen, the byte, and also the masks for working with that pixel. You can see it here. Now our screen base is at memory address 0 and each line is 128 bytes. So if we've got B and C as an XY position, basically what we need to do is multiply the Y position by 128, which we do by just shifting the bits ones to the right in a 16-bit value here. So we're shifting 1 bit out here of H into the accumulator. We're then ORing in the X position and we're loading that into L. So now HL is the offset for the memory address based on a 0-based screen, which ours is, for the pixel that we want to change. So that's got the byte position. We now need to work out how to select one of the 2 pixels. So what we're doing here is we're taking the bottom bit of B here, which is the pixel within a byte, so either the odd pixel or the even pixel, and then we're using a lookup here, and this will mask the left-hand side pixel or the right-hand side pixel, depending on which of those 2 we want to change. So we're loading in a mask for the pixel that we want to change into E, flipping the bits and loading a mask for the pixels we want to keep of the current screen settings in D. So we've got those 2 there, and that will be what we're going to use. Okay, so that's now got our data to work with the screen pixel. What we next need to do is we need to convert the color that we want to set the screen pixel to the correct position for the pixel we want to change, and get color mask num is going to do that for us. Now what we're doing here is we're actually masking the bottom bits here, and then we're shifting them to the right, basically moving them into the opposite position, and we're ORing in the original value. And what that will do is it will set both nibbles to the same original value. That will effectively fill the byte with the color, and that's what we've done here. We then AND it with the E value, which we've set here, and that is the mask for the pixel we want to change. So now E will contain the new pixel we want to put in. We then read the current byte from the screen. We AND with D, that removes the pixel we want to change, keeping the pixel we want to keep, or in the new pixel, which we've coloured here, and we save that back to the screen, and that has now set the pixel that we wanted to change. Now this version uses B and C as the X and Y coordinate and D as the colour. This version's the same, it just uses HL and DE and A as the colour, and this is just better for the line drawing routines basically. So that's what we're using there. Now when we want to read in from the screen, it's almost the same. We use point. This will read in from BC, XY position. We're using get pixel mask again. That's selecting the screen address, and we've got E as the mask to mask out the pixel that we want to look at. So we're reading in a byte. We're masking out the pixel we're interested in, and then we're going to convert that to a color mask using this function here, almost the same as before. So we've now filled the entire byte with the color. So what we're going to do next is we're going to use the color lookup, and that's here, and this is basically 16 bytes that represent a byte with both pixels the same color, and we're comparing to these to find the one that matches what we've now got. So that will effectively work out what color the pixel we looked at is, and it will return that just here, because once we've filled both pixels of the byte with the same color, it will now match one of these 16 here, and that will return the color. Now you could do this in another way. You could shift the nibble of the color value to the right if required, and you could get a common color in that way. It'd probably be a little bit easier. This is actually very convenient for me to port to multiple systems, so that's why I do it this way, but it's probably not the most efficient. Isn't a problem for this game though, because we literally use the point command about 3 times per loop, so it's not a speed problem. And then finally we just got a clear screen routine here, which is just wiping the screen, and the common code there, and that's really all there is to it. Now that's the end of this episode. We've covered how to do some pixel plotting on the Sam Coupe. We're going to be looking at the ZX Spectrum another time if you're interested in the Spectrum, because I know the Sam Coupe and the Spectrum have some commonality and some common fans, so hopefully if you're interested you'll stick around for that. Of course, as I said, you can go to my website, you can get the source code for today's game, and you can use it in any way you want. I really don't care, have fun with it if it's any use to you, and if you want to make the game better, go ahead. I'm sure there's lots you could do with it. Anyway, whatever you do, I hope you have a lot of fun with your programming, and I wish you all the best with the Sam Coupe and your Z80. Thanks for watching today, and goodbye.